My name is Grace Ingram. I am a senior studying biomedical engineering at Buchanan University, and I'd like to discuss the research I've been working on. First, I will walk you through the key points of my presentation. Collagen is a major load-bearing component of connective tissues. Therefore, it is important to study its properties. Structured polarized light imaging has been developed to study the structure of thick collagenous tissues, but this method is slow because it does not allow for imaging of tissue dynamics. Our goal was to develop high-speed structured polarized light imaging to study tissue dynamics. We used a special camera that images 4 polarization states simultaneously. We synchronized high-speed pattern projection and imaging and achieved an image acquisition of 75 frames per second. To demonstrate the capabilities of high-speed structured polarized light imaging, we imaged a rotating chicken tendon and uniaxially stretched pig scleral tissue. And we demonstrated that tissue movement and deformation can be continuously imaged and tracked at 75 frames per second. So let's get into some details. Studying collagen helps us to better understand tissue biomechanics and pathophysiology. Polarization-based techniques have been used to study collagen, but polarized light imaging of thick tissues has been challenging due to strong tissue scattering. In order to overcome this challenge, structured polarized light imaging has been developed. This technique replaces uniform planar illumination with structured light illumination. Structured light illumination, as shown in this diagram, projects high-frequency spatial patterns onto the specimen in order to limit imaging depth and suppress background noise. Therefore, we're able to get a good image of just the surface of our sample. Here we see how structured polarized light imaging has been applied before to characterize the fiber structure and orientation of an optic nerve head. With structured light illumination, the structure of the cornea fiber network is more clearly observed. Structured light illumination is slow, though, because it requires 12 images to be obtained. First, reflectance images are obtained from 3 different projection patterns. With these reflectance images, one single image can be obtained that only has information from the superficial layer of the tissue. Then this process is repeated for all 4 polarization states to ultimately be able to calculate fiber orientation and other properties. Because of this lengthy process, we cannot view the dynamic behavior of the tissue specimen. Our goal then was to develop high-speed structured polarized light imaging, and this photo shows our imaging setup that we developed. You can see a digital light processing projector, which generates the high spatial frequency light pattern onto the sample, and then you can see that the camera images our sample. Our camera is special, though it is capable of imaging 4 polarization states simultaneously, therefore the required number of images is reduced from 12 to 3. We synchronized the high-speed pattern projection and imaging to achieve an image acquisition of 75 frames per second. Then we conducted rolling image processing to achieve the same rate for visualization. We demonstrated the performance of our setup by imaging a rotating chicken tendon. We can see its fiber structure clearly, with horizontal fibers running across the base and then beginning to increase by small angles as we look further up the tendon. We also quantified the chicken tendon's fiber orientations by corresponding them to a color wheel, so the horizontal fibers at 0 degrees correspond to a red color, and as the angle of their orientation increases, they begin to appear yellow. We plotted the fiber orientation lines and of the image, and the data agrees well with the fiber structure. Even while rotating this image, you can see that there is accurate quantification of collagen fiber orientation, and we have continuous tracking of collagen fiber orientation and visualization of the fiber structure. This video was obtained with an image acquisition and video playback speed of 75 frames per second, the maximum acquisition rate our camera would allow. We also uniaxially stretched pig scleral tissue. We quantified both the fiber orientation and the fiber structure with and without structured polarized light imaging. Fiber orientation without structured polarized light imaging shows random, abrupt changes in the fiber orientations, whereas with structured polarized light imaging, improved quantification accuracy of fiber orientation is observed. Next, we see that the fiber structure without structured polarized light imaging is not very clear, whereas with structured polarized light imaging, the contrast and visibility of the collagen structure is improved. And in this video, which we achieved at an image acquisition and video playback speed of 75 frames per second, you can see the stretching of the scleral tissue. The change may be subtle, but they are deforming, and to better visualize the deformation, we generated a deformation path in a region of interest. We see that the deformation paths are region dependent. So we develop high-speed structured polarized light imaging using advanced projection and detection strategies, and this method preserves advantages of conventional structured polarized light imaging. It is valuable for studying soft dynamics and biomechanics. I would like to thank my PI, Dr. Ben Yang, and my peer, Benjamin Bernarding at Duquesne University, and our funding provided by Faculty Startup Funds at Duquesne University, as well as Dr. Ian Siegel and Po Yi Lee at the Ocular Biomechanics Lab at the University of Pittsburgh. And thank you to my audience for your attention.